I will start with a quick introduction on the state of AI in healthcare at the moment. Then I will discuss the question answering systems in details. Then we move on to large language models, the term that you hear the most these days. And then we talk about the RAG, or the Retrieval-Augmented Generation architecture. I know that we have time for QA at the end, but feel free to interrupt me if you see that you have something is unclear. If you have question, you can interrupt me and you can ask your question. It's okay for me. Okay, we all know the potential of AI. Actually, it's becoming the focal point of interest in everything in our day-to-day life. And we as scientists, you as healthcare professionals, you also want to benefit from it. You want to integrate it in your research, in your work. And our objective is simple. We want to help our patients. We want to help our medical experts to make better decisions. There are several areas, of course, that AI can help, like diagnostics. We can use machine learning, predictive models to identify disease. For example, cancer prediction, for example, diabetes prediction, or other predictive tasks. Or we have some advances of deep learning, advanced deep learning models in medical imaging, analyzing MRI images, CT scan images, radiology images, and so on. We can also have them in treatment, especially personalized treatment based on patients' historical data. And of course, as assistant systems. I think you all know the terms like decision support systems, expert systems, because you have been working with these systems for a long. And question answering systems are some sort of assistant system, AI-driven applications that can help us for certain tasks, which is the topic of today. So I'm going to take you back to the beginning, to what is question answering system in details. And then we see how we can put everything together to reach to explaining what is the RAG architecture. So by definition, a question answering system is simply an application designed to answer to user queries or to user questions. You have all used these tools if you ever use a search engine, for example, like Google. You input your query, your question, and the system responds give you a response in terms of a collection or a list of web pages. The core of all these question answering systems, like for example search engine, is what we call an information retrieval system. And all these information retrieval systems rely on something which is called a knowledge base or a data source. In case of search engine, you can see it as a collection of web pages. You submit your query on Google, for example, on the search engine, and then the retrieval component tries to search for the most relevant documents, in this case, web pages, to your query, and then gives you or provide a list of candidates for you. So this is the idea of information retrieval. To better understand this information retrieval system, I'm going to very briefly talk about the two major techniques that we are using in document retrieval and to solve this problem. So essentially what we have a query and we have a set of documents. Here in case of, for example, search engine, these documents might be the web pages. We are looking for the most relevant documents among the documents that we have in the collection. To put it simply, what we can do, we can say that we are identifying all the unique words that we have in our collection, in all the web pages that we have. Let's say, for example, we identified n unique words. We save them somewhere, and we call usually this collection of unique words a vocabulary. Now you can see your query as some of the words from your vocabulary. For example, in this query with 3 words, I have, for example, word 1, word 2, word 10 from my vocabulary. It's the same for the document. So each document can be seen as a sequence of some of the words from your vocabulary. And if you are looking now for the relevant document, simply you can do a term matching or a word matching. Sometimes these words called tokens or terms. So we can simply do the term matching. For example, the document on the right here has 2 words out of the 3 words that I have in my query. So this document on the right is probably relevant to my query. This is a very simple idea, and it's called Boolean matching. We can go a bit further, and instead of using the words, we can use a numerical representation for the queries and the documents. How? A simple idea is this. Imagine that you have a query with 3 words, for example, capital of France. So out of the n words in your vocabulary, we have these 3 words in this query. You create a vector with the dimension of n, which is your vocabulary size, and then you put ones for all the words that you have in this query. For example, word 1, so at position 1 and 2 and 10, you put 1, and you have zeros elsewhere. So somehow now we have a new representation for this query, a representation of using a representative which is a numerical vector of only zeros and ones. And these kind of vectors are called sparse vectors because they have many zeros, and that's why all these techniques are called sparse retrieval techniques. Now, this can be seen as a new representation of your query. Now you have a numerical representation. So you can do the same for all the documents that you have in your collection. So now you have a numerical representation for your queries, for your query and for your documents. Now you can simply use any search algorithm, like for example cosine similarity, to search in this space, in this vectorial space. You can now go beyond that and say, okay, we are not only relying on the presence of the word in queries and the documents, because not all the words, we know that not all the words in queries and the documents have the same importance. So the frequency of the words, the importance of the words are also important. So we have several algorithms here to go beyond that, and just by not only considering the presence of the word, and just also considering, for example, the importance of the word in a document. So instead of having ones and zeros in these vectors, we might have some other values. Still, we have a numerical representation of the queries and the documents, and we are searching in the space of the words to look for the most relevant document. So the whole techniques here, like for example TF-IDF or other terms that you might heard or you might not, all of them are searching in the space of words for the most relevant document. But we can go beyond that. We can say, okay, beside that, beside, for example, only these frequencies and the importance of the word, also the meaning, the semantic, and the relationship between the words are also important. I give you an example. For example, if in your query you have the word car, and in one of the documents we have the word vehicle. So based on the technique that I said, that I just explained, we might not find this query relevant, this document relevant, because we have car in the query and we have the vehicle in the document. But we know that these two terms are synonym. So now we are going beyond that. We are trying to find an idea. We are going to try to somehow search in a new space, where we're also considering the meaning and the relationship between the words. So the idea is very simple. We are using some sort of embedding techniques. We have some sort of mapping techniques, usually a neural network. And we are embedding our documents and our queries into a new space. So for each document and for each query, now we have a new vector representation with an arbitrary dimension, for example, m. But we know that in this new space, we are capturing the semantics and the relationship between the words. What it means, for example, if you have two documents which are similar together, for example, document 1 and document 2, the embedding vectors of these two documents are close now in this embedding space. So, and then now the idea is the same. Again, now we have embedding vectors instead of having those vectors that we had before, and we are now doing our search in this embedding in this embedding space, knowing that we are also considering the relationship and the meaning of the words. So these two techniques, sparse on the left and the dense on the right, are the two major techniques that we have in information retrieval to extract the relevant documents from a collection of documents based on the query given by a user, for example. Now knowing that, now we can say what is an information retrieval question answering system. Basically, we have the information retrieval part, which I just explained. But often in these systems, we have other components. For example, document reader. For example, a ranking component. Why? In case of, for example, search engine, when once you get the results out of the model, for example, all the relevant web pages, but you want to sort these web pages. You want to rank them based on their importances and to put the, for example, the most important one at the top. In some other application, you want to format your output using a specific template. You want to present your output, your answer to the user within a specific, for example, template or format. And we also have many other components at play here in this system, in this information retrieval system, to ensure its coherence and its reliability. For example, we have question processing techniques. We are not just directly using the question or the query of the user. We are trying some techniques like query rewriting or some other techniques here to enrich the query to help the model better retrieve the relevant documents. Or we are using several other efficient indexing techniques for a fast search among this large collection of web pages. For example, when you are searching something on Google, you see that in milliseconds, it will search the entire web for you and give you the result. So there are some indexing techniques help Google with that. So this is an overall what we call an information retrieval question answering system. Now let's cut and let's talk about something else, something that you might know: large language models. So what is large language models? Large language models, by definition, again, there are some sort of text generation model, text generative models, and these generative models are a class of machine learning models that can create new content. And we know that not these models are not new. We had them for a long time, but particularly they gain interest after ChatGPT because we have seen a workable example. So basically what they can do, these models they can generate text. How they can do it? By seeing a lot of examples. So usually I use this example. For example, imagine someone who has read all the books in a library, or someone who has seen all the web pages on the internet. So this individual, this person, not only understands what is a language, what are the structures and the rules of a language, but can also memorize all the content and the knowledge he has seen. So LLMs, you can see them like that. So these models try to track all the relationship between the words, between the sentences, with all the documents they have seen, a vast amount of data. And then they saved all this information into their parameters. So you can see them now as huge computational machines that can generate text. Sometimes we call them text completion models, because what you can do with them, you can give them some text, some input. In this case, usually we call it a prompt, or it can be a question, and then you will get your answer. So because they can complete your question and by answering it, so somehow we can see this LLM as question answering models. And researchers, especially NLP researchers, natural language processing researchers, believe that LLMs are going to shape how, or to change how in future people are seeking for information. Okay. Now let's make a comparison. If you take a query like, if you take a search engine like Google, and if you use a query like this, what is the capital of France? Probably if you click on search, you will receive some relevant web pages where you can find your answer in those web pages. So it's up to you then to click on those web pages and then find your answer. This is what we call an information retrieval question answering system. But if you do the same in a model like ChatGPT or in other generative models, which I think you have all tried it, you can direct it. The model will provide a direct answer to your question. For example, the capital of France is Paris. So we can see that these LLMs can be highly efficient in question answering. Now the question is this: can we use it? Can we use these models for specific domains? Can we use them, for example, for domains like medical domains? To answer it, we need to understand something. Models like ChatGPT or other, what we call them, open domain generalized LLMs, they have been trained on various data sources from different data sources on different topics. Yes, they have a broad knowledge of the word, and yes, they can answer questions on multiple topics, and yes, they can answer your medical questions, but they might not perform well sometimes due to some problem, due to lack of some domain knowledge. I think you have all tried, for example, models like GPT or LLMs for your field. You all have some examples that these models are not working as they should, and there are some reasons for that. The most important one is what we call the hallucination. If you are asking this model some question, if they don't know the answer, they might making up some stuff. And in certain areas, in certain domain like medical domain, where for example accuracy, reliability, transparency are your strict requirements, so you cannot simply rely on this model. I said transparency. For example, what is important for us, for example, what is important, for example, in application, if you are when you want to use them for medical question answering, what is important for you is you need to know why the model is saying what it is saying. You also need to have the references, and these models cannot provide that at the moment. And then so the other thing which is very important is the outdated information. You don't know what on which data set, on which data source that these models have been trained on. And maybe the data source that these models have been trained on, the medical, for example, data set that you have in your mind might be outdated. And several other problems that we have this problem. So what we want, we know that these models are quite capable, so we like it, we want to use them, but we want something more focused. We want something more specialized in the domain that, for example, we want to work. For example, in our case is medical domain. So to do that, there are several solutions. Again, I'm not going to go into these techniques, so I'm not going to go into details. Just I'll put the solutions here for you to have their names. The first solution to use large language models for your specific task, for example, medical task, is called pre-training. What we can do here is, okay, we say we take an LLM, but we are training it on our specific data sources, on the data sets that we choose. For example, on our Mimic dataset, on MedQA dataset, on UCMLE dataset, on for example, on the publication on PubMed. So you train your own LLM on the dataset that you like. It's good, it's going to work, but it's quite costly in terms of money and time. I'm giving you an example. For example, if you take, for example, this Google Palm model, for example, Palm model is like the Palm for Google is like GPT for OpenAI. So I think it cost 9 million euros for Google to train this model. Not sorry, $9 million for Google to train this model. So it's quite expensive, and we might not also have the computational power to do that, to train these models. But here, just for you to give you some examples, for example, on the examples that I put here for you, PubMed BERT is just a language models trained on PubMed dataset. Clinical BERT is a dataset, it's a large language model trained on Mimic dataset. BioBERT is a large language model trained on both of them, PubMed and Mimic datasets. So the other technique is fine-tuning. You are not going to train the entire model. You're taking an existing one, but you try to tweak it. You try to adjust it, modify it to your need. You tell the model, yes, I have these data sets. I also want you to memorize them. So also try to adjust your parameter based on the information on this data set, in this data set. This is what we call fine-tuning. It's less costly, but still you need to train the model. You need to provide a good data set for them. And there is a problem here. There might be some problem sometimes with this fine-tuning is when you are teaching your model new stuff, the model might forget what it already knows. So it's a known problem. And the third technique to use these large language models for your specific need is called prompting, which is the easiest technique here, and which is the most convenient one and the less costly one. The overall idea is to guide your model, to guide your LLM through certain steps, to walk your LLM through certain steps to reach to the correct answer. There are several techniques here. We are not going to discuss all of them, but the one that we're particularly interested in talking about is what is called Retrieval-Augmented Generation, or in short, it's called RAG. So it's some sort of prompting techniques to use large language models for your specific need. Okay, I hope you're all still with me. So what we said we have information retrieval question answering systems that are working based on a knowledge source. And we said that we have large language models. We can see them as question answering systems, and they are quite powerful in text generation and language understanding. So the RAG tries to combine these two ideas together. So let's see how. In this architecture, we have three components. The first component is the retrieval component, and it is exactly what we have seen in information retrieval question answering systems, a document retrieval system. But in your case, in medical case, now the data sources, you choose the data sources. You say, okay, I want, for example, to use the guidelines that I have. I want to use my textbooks. I want to use, for example, these articles from PubMed. So you choose the knowledge source. Then, instead of using, and then you have a generation part, which is exactly what we said about LLMs, is large language model. And now we have an augmentation part. You, instead of now feeding your query or your question directly to your LLM and seeking for answer, now you're somehow augmenting your question, you're augmenting your query with some additional information extracted from the knowledge sources that you provide. Somehow you are guiding your LLM, enhancing your LLM with some additional information, additional recent and reliable information that you provide. So you tell the LLM, if you want to answer this question, use this information, use these knowledge sources, use these knowledge sources. So what is happening here? We are mostly relying on the reasoning ability or reasoning power of the LLMs, the language understanding of LLMs, and not only memorizing, for example, the texts. So we are somehow combining the power of the two worlds, yes, the information retrieval system and the language generation system. All the components in this RAG architecture, the retrieval part, the augmentation part, and the large language model, the text generation part, can simply be optimized. So you can optimize the first part, then the middle part, or the last part. So the model is simply adaptable for your need. The output of these systems are explainable, because when the model provides some answer for you, you can also ask the model for the references, from which reference you provide this answer. So you can simply rely on the output. And the system is scalable. So anytime you want to add resources, you can simply add the resources to your knowledge base. You don't need to change a lot. You don't need to change the entire system. So I told you that all the components here can be optimized, the retrieval part, the generation part, or the augmentation part. But you can also use these systems for your application exactly as it is, without optimizing any parts, which is called frozen RAG. We are using the system and we are not trying to optimize any part. But as I told you, you can also try to optimize any part, then which will be a bit more complicated, but it is possible. If you look into literature, you will see that for the past 2 years, since 2023, we have seen a rapid development of RAG architecture in many domains, especially the medical domain. So what we did a scoping review on all the papers on Web of Science, IEEE, and PubMed on using RAG, this architecture, on medical datasets. And we have seen a lot of papers, more than 1,000 papers. And then this, after some screening and selection, we at the end, we ended up with 40 papers. With 40 papers, which whatever I'm going to tell you after this is based on those 40 papers. So we have seen many applications of RAG in many domains, many specific domains of medicine. For example, just one for diabetes care, one, for example, for answering only question on rare disease. And when we look into these systems, Most of them created for clinical experts, for healthcare professionals. And they are going to use this system as clinical decision support systems. So I give you an example. For example, you imagine a patient, a physician, and a patient. So the physician simply input the patient's symptoms and the physical, for example, examination information and the lab reports and the family history in the system. And the system provides some information, some recommendation for the diagnosis, for diagnostics test, for the even maybe even for the treatment. So what is important for us to know about this RAG system is they can access much more data, a lot more data, than a single, for example, medicine can see in their entire life. So in a fraction of a second. So they can be really efficient for your search. I'm not sure, for example, exactly what is your domain, what you are doing, but for example, usually if we have if a medicine have see a new rare cases, not an unseen cases, usually they need to go back to the guidelines, to the textbooks, maybe to the recent publication, and to look for the answers. So this system can speed up that process a lot and can help you a lot. And we have seen other applications of them, for example, just for patient education, maybe as chatbots, just for example, to answering questions about, for example, their problems or about a specific thing, for example, how to cure your diabetes. And we can also, and then also the researchers can use them for their research. At the moment, one limitation of these systems is their evaluation. It's quite difficult to evaluate them because we don't have a unified evaluation framework. But for each system, they need to evaluate their system on their own, and they can do it in automatic manner using, for example, a question database. So you have the correct answers, and now you are comparing the model responses to the correct answers. Or you can use experts, for example, to assess the responses generated by the model, for example, for the accuracy, for the reliability, for the safety, which is a bit costly because you need to pay for these experts. The other limitation of this system is might be the knowledge source. At the moment, most of the systems are created based on textual knowledge sources, but you can simply think about other type of other modalities for knowledge sources, like for example images, or like graphs, which is an active research at the moment. As I said, all the components can be optimized. The retrieval component, especially, is if you optimize your retrieval component of this system, you will get much better results depending on your for your application. And as I said, there is at the moment there is not a unified framework for the evaluation. We don't have large question databases to evaluate these models. And the cost of the training is very also important, because if you are using closed source LLMs, like for example for answer generation, like for example GPT models, you need to pay for the queries, you need to pay for the answers. But of course you can use open source LLMs, which might be free. Okay.